Hello and welcome to AI HDL, a competition like no other, where you will utilize AI to create code that will become computer hardware. In this competition, students will be designing a digital stopwatch. You'll be using AI tools like ChatGPT to assist with generating Verilog code for this project. Once you've written your code, you'll test it in simulation software called Vivado, ensuring that the logic works as expected. To showcase the functionality in real life, you'll use a digital hardware platform called an FPGA, specifically the Basis 3 board. As participants progress, they'll gradually add more advanced features. Undergraduates will focus on basic features, while graduate students will be implementing more complex functionalities. Milestones will be set to check progress and keep development on track. After creating these modules, we combine them into one system on a chip, or SoC, that acts as the watch's brain. Once the SoC is designed, it is sent to the factory to be manufactured. The chip is then placed inside the watch, connected to other components like the screen. Without this process, your watch would just be a fashion accessory. Vivado is a powerful software suite used for digital circuit design, simulation, and programming, especially in FPGA development. It supports HDLs like Verilog, allowing designers to write and edit code to define circuit behavior. With Vivado, users can perform synthesis and implementation, converting HDL code into optimized designs ready for FPGA hardware. This suite also includes simulation and debugging tools, which help validate and troubleshoot designs before programming. Overall, Vivado plays an essential role in transforming digital design concepts into reliable, high-performance hardware. In this demonstration, we'll use Vivado to develop a digital watch by implementing several key components. First, we'll create a clock divider module to slow down the system clock, ensuring other components operate at a suitable frequency. We'll also add a button debouncer, which filters out noise from button presses to ensure stable inputs. For output, a 7-segment display module will control the digits on our Basis 3 board, managing digit multiplexing and segment illumination. Together, these components will be integrated into a top-level module, alongside a digital watch module to help handle stopwatch functions, and we'll use a testbench to simulate and verify the complete design. The first module we will be generating is a clock divider module. When thinking of a clock, most people think of a standard 12-hour analog clock. However, the clock used in computers can be millions of times faster than these regular clocks. So, we must divide the frequency of the system clock to create a slower, more manageable signal for timing other components.
We will now demonstrate how to create the clock divider module. Press Add Sources, Add or Create Design Sources, and Create File. Once here, in the file name bar, you can type in clock_divider. After doing that, press OK and finish. You can press OK on the next two menus. And as you can see, after doing that, the clock divider module file will appear under the design tree under Design Sources. Double-clicking on it will open up a text editor where you can edit the clock divider module contents. We will now copy and paste the ChatGPT code that we were given into this module to create a functional clock divider module.
Next, we will implement the button debouncer. Most of the time when you press a button, the signal simply switches from 0 to 1 or vice versa. However, occasionally the button will bounce, causing the signal to rapidly change between 0 and 1. A debouncer takes this erratic analog signal and turns it into a singular, constant digital signal. The final module we will create is a 7-segment display. As seen on the image, a 7-segment display is a simple way to display numbers by controlling different lights. This 4-digit 7-segment display needs a module so that the digital watch can easily interface with it.
We will now generate the button debouncer and 7-segment display modules. Click Add Sources, Add or Create Design Sources, and Create File. You can name this file Button Debouncer. After doing so, press OK and finish. Doing this will create a button debouncer file under the Design Sources tree. If we double-click on this file, it will open it up in a text editor, and we can take the ChatGPT code we were given and paste it in. This will create a button debouncer module. After doing so, if we go to the Add Sources button under the Project Manager, Add or Create Design Sources, and create a file, we can create another file and name this one 7_segment_display. Press OK and finish. This will create the 7-segment display module under the design sources tree, and we will take our ChatGPT code and paste it into this file.
So, up until this point, we have generated only individual support modules for the project. However, none of these modules can actually communicate with one another. This is where the top level comes in. The top level design integrates and connects all submodules, handling the overall system's inputs, outputs, and internal connections.
We will now generate the top level design file. Go to Add Sources, Add or Create Design Sources, and Create File. We can name this file top_level and press OK. Press Finish, OK, and Yes. This will create the top level module under the design sources tree. If we double click on it, it will open it up in the text editor, and we can paste our ChatGPT code into the module. After doing so, you will see in our design sources tree that the button debouncer, 7-segment display, and the clock divider module have all fallen under the top level design module. This is because the top level design encompasses all 3 of those modules in its design. Now, if we go to the top level design module and scroll down, you will see a placeholder for where we will input the Stopwatch module once we have created it.
So, we have a top level design that can debounce a button input, divide a clock signal, and can display an output using the 7-segment display. However, the goal of the design is to create a digital watch, and we currently have no functionalities that a digital watch may have. To solve this, we'll be generating a stopwatch module using the prompt shown on the slide. Once the module has been generated, it is not actually integrated into the top level design, so we must prompt our model to add the stopwatch to the top level.
We will now generate the Stopwatch module. If we go to Add Sources, Add or Create Design Sources, and Create File, we can name it Stopwatch. After pressing OK, Finish, OK, and Yes, you will see the stopwatch file get created under design sources. It will appear outside of the top level hierarchy because the top level design does not include the stopwatch module yet. If we double click on stopwatch, we can paste in the ChatGPT code to create the stopwatch module. Now, because the stopwatch module is not being called in the top level design, it does not fall under the top level hierarchy. If we double click on top level to open it up in the text editor, scroll down to where the placeholder is, and paste in a call to the stopwatch module, you will see that the stopwatch module will now fall under the top level design in the hierarchy.
In order to test our final project, we need to create a test bench. We can use the test bench to simulate the inputs and outputs of the system and see how it behaves in different states. Using a behavioral simulation, these inputs and outputs can be visualized into a waveform, and this is very useful in debugging. For the purpose of this project, mentors will assist in designing the test benches.
We will now create a test bench for our top level design. If we go to Add Sources, Add or Create Simulation Sources, and Create File, we can create a file named top_level_TB. TB stands for test bench. Now if we press OK, Finish, OK, and Yes, you will see under the Simulation Sources hierarchy that a new file named top_level_TB has appeared. If we double click on it to open it up in the text editor and paste in the test bench that ChatGPT has created for us, we now have a working test bench. You will see under Simulation Sources that the top level design has now fallen under the top level TB. This is because the top level test bench calls the top level design when a simulation is run. To run a simulation, we will go to Run Simulation, Run Behavioral Simulation, and you will see a waveform appear on the right side of your screen. If we minimize some windows and drag the window to be wider, we can see a larger amount of the waveform. In order to see the entire waveform that was generated from our simulation, we can press the Expand button. Here you will see a clock, a reset, button 0 and button 1 inputs, the 7-segment display, output, and the anode output. You can see that the clock is running extremely fast. This is why we have a clock divider module to make sure that we divide down that clock signal so that our modules can use it properly. We also have a button 0 input. However, as you can see, it went off to the side of the simulation. So if we run the simulation for longer, you can see that after the button 0 input has finished, the stopwatch module has begun counting. Now, These values don't make much sense to us. However, that is because these values are used to light up the 7-segment display. If we go into the Stopwatch module and pull out the time values that are inside of the Stopwatch module and relaunch the simulation, you will see after running the simulation for longer that our stopwatch is functioning properly and counting. If we run our simulation for a little bit longer, you can see that after pressing button 0 again, the stopwatch module pauses, and if we press button 1, it resets. Here's a demonstration of our code being run on the Basis 3 board. Once again, we would like to thank all of our sponsors and collaborators.